This time I'm going to find the solid revolution created by the graph y equals x squared, bounded by the line x equals 3. Okay, that's a vertical line that cuts through here at 3 on the x-axis. Notice that this point up here will be the point 3, 9. We might need the x, we might need the y, and the x-axis. So I'm looking at this region, rotating that around the y-axis, okay? So if you notice, I've got a straight line on this side. If I rotate around the y-axis, the outside of this thing is going to be flat. The inside is going to be a curve. So it's kind of a flat-sided glass with a curved inside, if you're trying to imagine what that looks like. And so we'll try to get some kind of visualization over here, but basically looks kind of like that. And again, it's completely being revolved around. Now, the game changes a little bit in this example because it's no longer solid all the way through. If it's solid all the way through, you could probably use discs. They work real nicely. Discs are a great way to do this problem, but you have to be careful because if you're using discs to do this problem, you'll notice the inside is cut out. Okay, and there are two ways to think about this. You can find that overall outside volume created by this line, and then you can find that inner volume that's basically being carved out, cut out, and you can remove that inner volume. Okay, that's one way to think about this. You can also think of this in terms of cylinders, and you can think, well, if I did a cross-sectional cylinder here, what's actually happening is you've got this outer cylinder here, and the inside is cut out. And so what you get is, you get this ring, okay, in geometry we call this outer ring here the annulus, and really we're stacking those rings, and if we can find the volume of those rings, starting with a very thin ring here and getting wider and wider and wider as we get down to the base, we can find the volume. So you find the volume of one of those rings by taking basically the volume, well, you can take the area of the base times the height, or you can take the volume of the outer cylinder and subtract the inner cylinder, because remember, this thing is really three-dimensional here. It's something more like this is what you're actually looking at. Okay, so you take out the inner cylinder and you keep the outer part. So it's the large volume minus the small volume. So officially, dB is equal to pi capital R squared h minus pi lowercase r squared h. Okay, there's a big circle radius and there's a small circle radius. We're subtracting that cylinder with the small radius from the big one. And then we add up those cylinders and it gives us the volume. That's the concept, okay? Or again, if you want to think of it as finding the outer volume and then subtracting the inner volume, same difference, okay? So, really just a matter of filling everything in here in the equation. Now the big radius, I am no longer going to try to draw cylinders here because I've got to have an outer cylinder and an inner cylinder, and it just gets very complicated to draw. I'm going to go with Forrester's approach. Forrester's approach is to draw the strip, okay? And that strip gets spun to create the cylinders that create these washers, is what a lot of books call this, washer method. So anyway, Forrester will draw the outer strip. Okay, and of course the outer strip is going to be drawn, it's representing the radius and the thickness basically of that cylinder, and it's going to be perpendicular to the axis of rotation. Okay, notice that length there, that radius, always stays the same. That's a constant, x equals 3. So as a result, when I fill this in, it's going to be pi times my big radius, always going to be 3, times the height, which of course is a dy, okay, minus pi times the inner radius. Okay, the inner radius is just if I drew my strip out to this inner graph. Okay, and notice that those values are changing there. There's an x-coordinate and there's a y-coordinate, but they're changing. Okay, in this case, the radius is represented by an x. So it's the radius squared times the height, the thickness of that strip, or the thickness of a cylinder, or of that washer, if you want to think about it there. And that's a dy. And this is telling me everything's got to be written in terms of dy, or everything needs to be written in terms of y, which is fine. Here I can take both sides to the 1/2. I know that y to the 1/2 is equal to x, so that's y to the 1/2. And basically I can go ahead and find my integral. My integral is the sum of these washers, if you want to think about it that way, starting at the bottom, adding all the way up to the top. Notice those are y values. It's going to go from 0 to 9. 0 to 9 of pi times 3 squared dy minus pi times x squared, and again I'm going to replace that with a y to the 1/2 dy. And again, you can break this up into two integrals, probably a good way to do it. You could factor out the pi's, obviously you could write that as a 9. Keep in mind, that first volume there is really just going to be the volume of a cylinder. It's got straight sides, okay? So, you know, the volume of the cylinder is pi r squared h. What's going to end up happening is the height goes from 0 to 9. There's your pi r squared, and that's what that ends up doing. So certainly you can do part of this problem without calculus, but for the second volume, obviously, you're going to need calculus, so it makes sense to use it for the whole thing. But that's the main thing. Larger volume minus the smaller volume, or you can think of it as basically that, you know, a cylinder, a larger outer cylinder minus a smaller inner cylinder, and then adding up those rings. Either way, great way to do these problems. But the key is, you have to use this approach. You've got a hole in the center, and it all comes down to that equation right there. Pi big R squared h minus pi little r squared h. This time I'm going to do a slightly more complicated volume. I have the equation y equals x squared. It's the region bounded by the vertical line x equals 3, which of course is right here. Rotate around the x-axis, or I'm sorry, bordered by the x-axis. So again, I'm looking at this region right here, and I'm rotating this around the line y equals -2, which of course is the horizontal line passing through -2 down here. So if this is my axis, what's happening here, if I rotated this around the x-axis, I would basically get a horn shape. What's going to happen is this is going to be kind of shaped like this, and then it's going to stop, and there's going to be a big hole in the center. So basically I've got this width down here, you know, this is all going to be empty space rotated around the axis. So basically you'd have another solid line down here, and then your graph kind of continues like this, and you get a big kind of circular thing, this thing being spun in circles with this flat-sided empty cylinder in the middle. Almost kind of like if you were a kid and you made a volcano with a toilet paper tube on the inside. Kind of goes up like that, and with the hole in the center. You know, technically it's going to look something kind of like this, with this open chute down the middle and going from there. Anyway, because this has a hole in the center, one approach you could use here is the disk method. And of course, we're basically taking, you can think of it as an outer volume minus an inner volume. You can think of it in terms of disks. You have one disk, you're subtracting the inner disk, you're getting the volume just of one of those rings, which are what cross sections are when you cut here. Picture's gotten complicated enough. I'm going to go with Forster's method just of using strips instead of trying to draw the outer cylinder and the inner cylinder in there, although certainly if you'd like to do it that way and if it helps you visualize it better, you can. Big thing here, there are two volumes here. You get that outer volume minus the inner volume. So my dV value here is dV equals pi big R squared h minus pi little r squared h. And I just need to fill in those values. So let's go through here. Okay, big radius here. And again, you always draw your strip in perpendicular to the axis of rotation. So there's my strip. Now, big radius. Normally that's an x, y point. But check it out. The radius is no longer the y value. Notice it's the y value and then continues to go down here. Okay? So think about that. You have an upper value, you have a lower value. How do you figure out how far apart they are? You subtract those two values. So that's going to be y minus -2. Okay, yes, I know that y minus -2 is y plus 2. If you want to write that, that's fine. And I guess visually it's this y distance plus that distance there, if you want to think about it that way. But in general, larger value minus the smaller value. It's always going to give you that length between those values. Okay, the radius gets squared, you multiply by the height. The height of that thing is that little thin width, and that's a dx. So I've got to write this thing in terms of x minus pi little r squared, okay? The little radius here of course, is only going to here. And of course, that little radius is going to stay the same every time. You know, technically that's 0 minus -2, which of course is just going to be 2 times the height. And again, the height of that thing, the thickness, is dx. So everything has to be written in terms of x here. It's going to be a big integral. Now, you're adding these technically washer-shaped discs, starting here, going over here. It's all written in terms of x. So you've got a starting x position, an ending x position, and you've got pi times, technically that's going to be y plus 2 quantity squared of dx. Sorry, this needs to be written in terms of x. So the y needs to be replaced with an x squared. Okay, minus pi times 0 minus -2 is just 2 squared. Okay, you could write that as 4 dx as well. You could break that into 2 integrals. Of course, you could factor out the pi's, but again, that's the basic setup. This time I'm going to find the volume of the region bounded by y equals x squared and y equals 3x rotated around the x-axis. If you think about this, y equals 3x, of course, is a straight line. Y equals x squared is this curve here. Again, you do need to verify which is on top and which is on the bottom. I usually kind of exaggerate my graph. I don't necessarily draw it to scale, so I can really see where those positions are. So here is my y equals x squared. Here is my y equals 3x. And of course my region is this region here. Now if that's rotated around the x-axis, technically you're going to get, you know, that line basically coming down here, and you're going to have that curve, and it's doing something like that. And this whole thing is being spun, so it's going to be kind of a, it's basically going to be, oh, you know what, I got this backwards actually. Let's see, the straight line is on the outside here, and the curve would look something kind of like that. What it's going to look like, it's going to be almost like a glass that has straight sides and then has a bulbous, has a curved inner side. That's kind of convex, so a little bit strange there, but flat outside, curved inside of that glass as you rotate this around. And again, you may want to try to draw some type of circular thing here so you can kind of visualize what it's going to look like. In this case, though, I'm going to focus on using the formula. Notice that the inside is missing, so you can either find that outer volume minus the inner volume. One way to think about that. The cross sections are cylindrical shells. Sorry, they're not cylindrical shells. Cross sections are washers. They're basically a cylinder with an inner cylinder cut out, if you want to think about it that way. So, of course, the formula for that is dV equals pi big R squared h minus pi little r squared h. Real simple formula there. And basically we just need to fill those values in. So dV is equal to pi times, now big R, the big radius here, again, you're rotating around this axis right here. Okay, so your radius is going to be coming from that. Forster draws just a strip to simplify things. So he draws the strip perpendicular to the axis of rotation. And you'll notice you have an outer radius and you have that inner radius that has to be subtracted to give you that volume taken out of the inside. Okay, so that's the point x comma y. Notice the radius in this case, your big radius is going to be a y value squared. Put those parentheses in. Okay, the height is the width of that thing. It's a thickness, or it's the height of that cylinder technically. That's a dx, telling me everything's got to be written in terms of x, minus pi times the little radius squared. Okay, the little radius, of course, is this thing right here. That's an x comma y, or you can call it an x2 comma y2 if you wanted to. But the little radius, again, is the little y coordinate squared times dx. Now, the big y value was coming from the outer equation here. In fact, you may want to go ahead and do your substitution at the time. That's that y equals 3x equation. The little y radius was coming from y equals x squared, and now you have your equation. This is all written in terms of x, So we're stacking these things up in the x direction. These intersect each other at 0, 0, and 3, 9. So going from an x value of 0 to an x value of 3. So 0 to 3, pi times 3x squared dx. Again, make sure you got your parentheses in there because you can get a 9x squared when you square that. Minus pi times x squared squared. Very easy to lose one of those squares, so be real careful. Dx, and certainly simplify that down. That'll be a 9x squared there. That'll be an x to the 4th. You could factor out x's, you could break into two integrals, but that's your basic setup.